Hey everyone, this is Mike Bartles from HEC. Within this presentation, I'm going to continue discussing the Clark-Unit hydrograph parameter regression equation analysis for the state of California. This video is part 3 within a series of videos devoted to the subject. As an overview of this presentation, I'm going to talk about how the regression equations were formulated, how the regression equations were parameterized, and how the regression equations were then validated. Same as before, my challenge to you is name that dam and write it in the comments below. 2 multiple linear regression models were considered within this study, as shown on the right. In both forms, y is the dependent variable, like time of concentration or watershed storage coefficient. A is a regression constant. x1, x2 are independent variables, and their watershed characteristics. And b1 and b2, so on and so forth, are unknown coefficients. The regression constant and unknown coefficients were determined utilizing the method of least squares. When using multiple linear regression with several watershed characteristics, some of the proposed characteristics may have little to no effect on the dependent variable of interest. When this occurs, these characteristics were removed from consideration. In order to simultaneously evaluate the effectiveness of the regression models and avoid overfitting, an adjusted coefficient of determination, called adjusted R-squared, was used. The nice thing about this metric is that its value increases when a new term improves the regression model more than would be expected by chance. Variables with p-values less than or equal to 0.05 were desired. However, this criterion was not the only determining factor when evaluating explanatory variables. Stepwise selection techniques were employed with adjusted R-squared and p-values to select the most performant watershed characteristics. Regression equations were first developed individually for each region, then attempts were made to develop regression equations for multiple regions that exhibited approximately the same predictive power. This was done to increase the sample size, reduce uncertainty in the results, and make the regression equations easier to apply. Models developed separately for regions 2, 3, 4, 6, and 7 were found to exhibit similar behavior. As such, they were combined to form a single model that spanned all 6 regions. However, Region 1, Region 5, Region 8, Region 9, and Region 10 could not be combined and still be performant. Scatterplots relating T sub C and R to the watershed characteristics were developed for each of the 10 previously mentioned regions using the ggpairs function from the ggally package in R. The resultant plots and information were used to make informed decisions as to which variables were most impactful. The watershed characteristics were considered to be error-free because of the computational accuracy of the GIS datasets themselves. However, the Clark-Unit hydrograph parameters were not considered to be error-free, and these errors could arise from numerous sources, including but not limited to boundary condition information, modeling techniques, and observed data availability. Clark-Unit hydrograph parameter error was included by including weights corresponding to the data availability. Locations with 15, 30, or 60-minute streamflow data were given a weight of 3. Locations with daily average and instantaneous peak streamflow data were given a weight of 2. And locations with instantaneous peak streamflow only were given a weight of 1. The various regression models developed for each region or set of regions were examined using several diagnostic tests to ascertain whether the models obey general assumptions of multiple linear regression. These diagnostic tests included checking whether a linear relationship exists within the model, residuals or errors are evenly distributed over the range of predicted values, residuals are normally distributed, and one or more residuals do not exert excessive leverage on the model. Now at this point, I'd show you the actual equations, but we can't share them due to their ongoing use by California DWR DSOD and the way in which they operate. I'm sorry. I can tell you that there were 2 equations developed for each region or group of regions, one for T sub C and one for R. Now if you work for USACE, please reach out to us and I can share them with you. Instead of showing you the equations, I'll share a cartoon about my spirit animal. Specifically, Greg is telling me how much he appreciates my enthusiasm for big dams. Now that regression equations have been developed, their accuracy needed to be quantified using a validation process, where hydrologic model results were compared against observed data. Specifically, hydrologic models were constructed for numerous independent locations that were not included when developing the regression equations. These models were constructed and parameterized using the same process that was previously described. However, Clark-Unit hydrograph parameters were estimated using the regression equations that were developed for the specific region of interest. Additionally, the Clark-Unit hydrograph parameters were then calibrated and compared against the predicted values in a separate iteration. We went back to the map of California and attempted to find 2 locations per region. However, only one suitable location was found within regions 5 and 8. There just simply aren't that many locations with observed data in those specific regions. This led to a total of 18 locations statewide with drainage areas ranging between 5 and 536 square miles. Here's an example of the validation process for the Cosumnes River at Michigan Bar. An HMS project was created for this location using GIS data, Clark-Una hydrograph parameters were estimated using the regression equations, and the precipitation runoff process was simulated for a large event to test how well the regression equations performed. As you can see, the predicted T sub C and R produced very good results at this location. This process was then repeated at the other validation locations. And here are two plots demonstrating the validation process for regions 2, 3, 4, 6, and 7. The first plot on the left compares predicted T sub Cs on the x-axis against the calibrated T sub Cs on the y-axis. Similarly, the second plot on the right compares predicted storage coefficients on the x and calibrated storage coefficients on the y-axis. The predicted T sub Cs and Rs for several validation locations displayed a slight overestimation when compared against the observed T sub C and R achieved through model calibration, but the validation results are well within the bounds of acceptability. In summary, within this video I presented how the regression equations were formulated, the tools and techniques that were used to parameterize the regression equations, and the validation steps that were taken to prove their applicability. In subsequent videos, I'll talk more about quantifying uncertainty within the regression equations, as well as an example application of the regression equations. Thanks for watching. I'll see you in the next one.